Okay, so in lesson 4.1, we're going to start looking at applications of the derivative. We've kind of seen them a little bit. We've seen some of the position, velocity, acceleration, the dreads things. But now we're going to talk about maxes, mins, and critical points. So you might recall in pre-calculus, we couldn't find the maxes and mins unless we were given a graph. We had no abilities. We knew approximately where they were at, but if we had the graph and something like Desmos, we knew there was a bump there. We knew there was a relative min or max. So for the first time, we're going to talk about actually finding them algebraically. So we're not going to necessarily rely on a graph. We're going to rely more on the algebra of it. Now, you might recall that I have shown you this graphic many times. So what was happening when to our tangent lines when our function was increasing? So the green ones. What's positive about the tangent? The slope of the tangent is positive when the tangents turn green. Okay, so it's increasing. The derivative is positive, okay? What do we notice about when it's decreasing and they turn red? What about the tangents there? The slopes are negative. What about when they hit a peak or a valley, when they hit that relative max or min? What is happening to the slopes there? The slopes have a horizontal slope, so a horizontal line, so their slopes are 0, right? And that line turns black. So for the first time, we can locate those exact points by looking at where the tangent, which is the same as the derivative, we can then locate those by finding the zeros. Now, sometimes we get something that is called a critical point. And a critical point doesn't always give us a max or a min. It might give us something eventually we're going to talk about called a point of inflection. But eventually, the derivative can give us lots of information. So first, let's talk about an absolute maximum. So a function has an absolute maximum at a particular point if it is the largest value over the entire domain. So f of c has to be the largest value. It is the maximum of the function. So of course an absolute minimum has the flip side of that. F of c would be the lowest point over the entire domain. So remember that absolute language tells us that there are no values that are bigger than or than that particular value. Some books use the language, they say global max and min. I most of the time am going to say absolute max or min. But if you see that language, it's the same thing. Sometimes we are going to call those extrema. I think our pre-calc book last year called them extrema or extreme values. So that's another language that you might see. They all mean the same exact thing. So extrema, maxes, and mins are all going to be the same question that you have to answer. So let's look at a graph and kind of analyze some stuff. Here's a graph. So if we look at this particular function, there is an absolute max f of d. Now this particular function only has a domain from some a value to some, let's call this g, I don't know. So its domain only goes from a to g. Don't expect there's not arrows on the ends, so it's not continuing in any sort of way. This particular function also has an absolute minimum. If a function has a domain on an interval, so if it starts at one value and stops at another, and if those endpoints are included, it will always have an absolute max or min. Some functions don't have an absolute max or min. But if a function is on a limited domain, so if it's on an interval from a to b, including a and b, it will always have an absolute max or min. Think about our parabola. A parabola has an absolute minimum. Our parent parabola has an absolute minimum at the point 0, 0. It doesn't have an absolute maximum, so that's okay. That happens sometimes. Think about our cubic function. Our cubic function has neither an absolute max or an absolute min. Now it has this strange flip over point, which we haven't talked about much, but that's going to be something that eventually we will talk about. We're going to start talking more about the curvature of the graph. We're going to start talking more about when the curvature changes, and that's going to become a point that's going to be something we will talk about. But don't expect a graph to have an absolute max or min. Because it doesn't have to have one. Now, an absolute max or min is not the same as a relative max or min. So remember, if we are looking at the hills of a graph, we're looking at the bumps of the graph, the highest point of the entire graph is considered our absolute max. So it's like if you're looking at, a mountain range and you're looking at Mount Everest, it's going to be the highest. But if you're looking at some other peak, it's a mountain, it's not the highest. So you have to look at what language they're using. Are they talking about absolute or are they talking about relative? So here is the definition of a local maximum. So a local maximum is the maximum on an interval very close to that value. So I think of it as one of our mountain peaks, but not the highest. Not necessarily the highest. So when we are near C, and that near C is kind of relative. I mean, it depends upon how big the function is. But if we're pretty close to it on each side of it, it is the largest value that is near C. It is the largest value of the function. And local minimum is the smallest value when we're near some value C. So let's look back at that original picture that we saw on the other page, and let's kind of go over what we know. So if we find every single mountain peak, so at B and at D, f of B and f of D are both considered relative or local maximums. So all mountain peaks are considered relative maximums. All valleys, so all valleys of some sort, so here and here, so f of C and f of E would be considered relative minimums. Now, when a function distinctly ends at this particular one, I said A and G, where the function particularly ends, can sometimes be included in the relative min or max sort of idea. The problem is you can't get an interval on both sides. So you really don't include those too much unless we're going to include those as the highest point or the lowest point of the function. So when you're asking for relative maxes and mins on the interval, don't include the endpoints. If they say, where's an absolute maximum of the function, we can include the endpoints. So first we're going to look at an example, and we're just going to look at some functions in general, and we're going to talk about where they have relative and absolute maxes and mins. So let's take a look at this. So if we look at our cosine function, so let's recall, does the cosine start at 0 or start at 1? Does the cosine start at 0 and go up or start at 1 and come down? Think about, here's the point on the inner circle. What's that point? That point is the point 1, 0. Do we use the x or the y for cosine? We use the x. So it starts at 1 and comes down. Remember? Okay. So if we are to graph this, let's assume this is 1. It's going to start at 1 and come down. Sorry, it's hard to see my lines here. Here's our cosine graph. One cycle of it, one period to the right. Let's do one period to the left here. Okay, so you have to remember that the cosine starts at 1 and comes down, and that the sine starts at 0 and goes up. It's just important to know that, okay? So let's talk about the relative maxes and mins. First, let's talk about the relative maxes and mins. So let's go with the maxes. All the things that I hit in blue are relative maxes. They happen to also be absolute maxes for this function. What is the absolute max value that a cosine will ever hit? 1. So remember, our sine and cosine, when it's the parent sine and cosine function, it is always cycling between positive 1 and negative 1, positive 1 and negative 1. So for this particular one, the absolute maxes occur where? Well, let's look. It occurs at 0, then at 2 pi, then at 4 pi, then at 6 pi, negative 2 pi, negative 4 pi, negative 6 pi. So all multiples of 2 pi. So how do we write that? Well, we just write 2n pi. And we assume that n is an integer. So that's the formal way to write. It's all the 2's. 2 pi, 4 pi, 6 pi, negative 2 pi, negative 6 pi, and 0. Okay? Now let's talk about the absolute minimums. If you look at those pi's, they're the odd pi's. 1 pi, 2 pi, 3 pi, 4 pi. So to write odd numbers is a little different. To write an odd number in a formal sort of mathematical way, those are the absolute minimums. That's 2n plus 1 is the way that we write an odd number. We talked about that a little bit last year, that you write an odd number as 2n, so an even plus 1. So it's 2n plus 1 pi when n is an integer. So that's the formal way. If you write odd pi's, even pi's, I'll know what you're talking about. Let's take a look at example 2. So you got to know your parent functions. So that's a parabola. Our parent function starts at, has a vertex at 0, 0 and goes up. It only has an absolute minimum at the point 0, 0. There is no absolute max. And then our cubic has no absolute max or min. Now we're doing these graphically to start, but then we're going to talk about how to do it algebraically in a minute. Let's take a look at example 4. Example 4, let's look at the graph. Now you might notice it's a 3x to the 4th. We know that should look like a parabola because the lead term is a positive coefficient with an even power. It should go up. There's going to be some bumps in it because of the extra terms. And if we were to look at it, it looks like this. Now, they only are caring about the function between -1 and +4. So they have a starting and a stopping point, a distinct starting and stopping point. When that occurs, we will always have a max or a min. Okay? If we take a look at this point here is the absolute maximum. It is at the point -137. Here's a relative max, a relative min, a relative, no, that's an absolute. Okay, let's mark them. This is a relative minimum at 0, 0. This is a relative maximum at 1, 5. This is a, well, we don't include it if it's not an absolute on the ends. This one here is a relative minimum. Oh, that's absolute. Sorry about that. 3, -27. Okay. So if you have the graph, finding maxes and mins isn't bad. But I want to be able to do all of these problems without ever having to look at a graph. So that's where we're going to be heading. So for this lesson, I want to start looking at things algebraically. So we need a little bit of some theorems, some ways, some rules that we are allowed to use. And so that's what we're going to do here in a minute. Okay. So one of the rules we can use is called the extreme value theorem. So I would abbreviate it EVT. So I'll abbreviate it EVT. Now this only works if we have a continuous function. So remember, if we could draw it without lifting our pencil, if you could trace it, you could cut a piece of string out and lay it on it, and you never had to cut the string. And it starts at one place and stops at another place. So only if we have a continuous function on a closed interval. So we're making a loop, we're including the endpoints. Only if that's the case, we will always be able to find an absolute max and an absolute min at some numbers C and D within the interval. They're always going to exist. There is always an absolute max or min if that's the case. So let's look at our examples, okay? Let's look at a function. Here's a continuous function. At endpoints A and D, or A and B, it stops. There's a C, that's a max. There's a D, that's an absolute min. There's an absolute max and min. Okay? So if it's shaped like that, you see where that happens. Here, the absolute max is within the interval. The absolute min is one of the endpoints. So this one had both of them inside the interval. This one had one of them on the outside. Here, where we have 2 points where there's an absolute max, that can happen. You might end up having duplicate maxes and mins. So having duplicates is okay. This one does not fall in this category. Why doesn't it? What's wrong with it? There's a break in the graph. It's not continuous. So we don't have to worry about this particular function on the interval from A to B. There's a break. We would say, well, we can't necessarily find a max or a min. This one doesn't have a stopping point at 2. No, there's an asymptote there. Does it? If that's an open circle at 1, it doesn't have a closed. Now, if we stopped here and here and only use that part of the function, sure, that's okay. But it has to be a continuous part of the function, and we have to have endpoints, or you can't necessarily find an absolute max or min. So let me just read this down here for you. It says, the extreme value theorem, EVT, says that a continuous function on a closed interval has a minimum or a maximum and a minimum value. But it does not tell us how to find these. Okay? So we're going to learn how to find them. So, because we've just been relying on graphs to this point, and I don't want to rely on a graph. So we need a method. We need something to go by. Now, we learned a little bit from that first graph we saw that every time it hit a hill or a valley, there was a zero. There was a horizontal. That's where Fermat's theorem comes into play. Fermat's theorem says that if a function has a local max and min, it has to occur where the first derivative exists and equals 0. Exists and equals 0. So, let's think about this for a minute. Where the first derivative doesn't exist cannot be a max or min. But if there is a first derivative that's equal to 0, it may be a local max or min. So let's think about the one, why does this one not have a local max or min? Well, for a moment, let's think about it for a minute. If we go back to this picture, let's go back to our little video. Let's look at this for a minute. This is a max. What color does it switch from? What color was it on this side? What color is it on this side? Our tangent lines. It goes from green to red, right? Right here, does it go from green to red? So all of the maxes, what happens to the slope of the tangents? They go from green to red. They go from positive to negative, right? Because it has to go uphill, turn, and then go downhill. Okay? Now I want you to focus on the minimum down here. It'll be back around here in a second. When we get to the minimum, let's think about what color change happens there. So now we're coming up on this median. What color are we? We're red. When it switches, now it goes to green. All minimums will be like that. Now, there's one other point here, and we're going to see it happen in a second. Over here near 0, we're going to see a black section. Is that a max or a min? No, it's not. So you see, that has a horizontal tangent, a slope of 0 for the tangent, but it's not something there. That point is a point of inflection, which we will talk about more. So not all zeros give you maxes or mins, but you'll notice that every max or min was a 0. Okay, let's go back. Okay, so let's just look at this for a minute. If we were to take the first derivative, let's remember our derivative rules. First derivative of that, we know. Let's think about where that's equal to 0. Right? We know the first derivative of that is 3x squared. And then when we set it equal to 0, we get 0, right? Now let's think about the graph, or the plus minus chart at 0. Would you agree that if we take and plug in -1 or +1, we get positive and we get a positive? So our slope of our tangent was going up, and then it just had a little bink, and it continued to go up. It's not a max or a min there. It's something different. So that's why it's not a max or a min. Let's look at the absolute value. We learned that the absolute value has a problem. It isn't differentiable at the pointy point. Remember that? Okay. So let's talk about what happens at pointy points. That is considered the absolute minimum of our function, right? Okay. But let's think of this as the piecewise function that you guys love so very much. It's negative x when x is less than 0, positive x when x is greater than or equal to 0. Piecewise function is always important when doing the derivative of an absolute value. If you take the derivative of negative x, we get negative 1. When we take the derivative of positive x, we get positive 1. There is a jump right there at 0. So the first derivative doesn't exist at 0, but we know it's a minimum there because that's the lowest point of the graph. So we have some things we have to continue to think about these first derivatives, where they're equal to 0, where they don't exist, all give us information. So, because we have to worry about where they're 0, where they might not exist, we talk about something called a critical number. A critical number is where the first derivative either is 0 or doesn't exist. So like in our absolute value, it didn't exist at 0. So we call it a critical number. A critical number can occur in two ways, where the first derivative either is 0 or does not exist. That's important to know. Now we can expand upon what we know about maxes and mins. Because of this critical number idea, we're going to expand that Fermat's theorem just a little bit. And we're going to say that a local minimum or a maximum or minimum will only occur at a critical point. It's got to be a critical number. A critical number is where we're going to find them. So now let's rely a little bit more on our algebra. Let's take a look at this particular point. And they're not asking us to categorize maxes or mins or anything. All they're asking us to do is to find the critical numbers for this function. So you were looking at where the first derivative either is 0 or doesn't exist. So let's take a look. Well, in order to do this function, we either can distribute in the x to the 3/5, which is totally legit, and then take the derivative, or we have to use the product rule. Which do you prefer? Which do you want to do? You want to do the product rule? Okay, so we'll do the product rule. So we remember the product rule, and so the first times the derivative of the second plus the second times the derivative of the first. So there's our product. Okay? So we are looking at two things. We are asking ourselves, where does it not exist? Where is it equal to 0? That's what we want. Where does it not exist and where is it equal to 0? Well, let's make that look a little nicer. Okay, let's make it look a little prettier. This is going to make it much prettier, but I'm going to do a little trick kind of factoring. I'm going to take out the lowest power on our x. Well, negative numbers are lower than positive numbers, so I'm going to do a trick. I'm going to take out that negative power. So to divide out a power, we have to subtract its exponent. So to divide out an x to the negative 2/5, we are subtracting the negative 2/5 power. When you subtract a negative, what do you get? A positive 2/5. So technically what's going to happen is a little trick here. We're going to take out a negative 2/5. And what it's going to do, it's going to make every single power that's there go up by 2/5. Because we're subtracting a negative 2/5, which is adding 2/5. And so what happens is 2/5 plus 3/5 is 1. And then we've got this. And then that went away because we took it out. Okay. By doing that little trick, we end up in the parenthesis having normal stuff, which is good. Now, let's think about some things for a minute. This is a negative exponent. Hopefully you remember that negative exponents should be in your denominator to make them positive. Now let's kind of mess with this a little bit. This is 3/5 times 4 and 3/5 times negative x. Okay, so we have a negative x minus a 3/5 x. And that's 5/5 and 3/5 is negative 8/5 x. And then 3/5 times 4 is 12/5. So I'm just adding them up. No, I don't like the fact that they're fifths, so why not multiply top and bottom by 5? I'm just making the algebra a little nicer. And so we get on the bottom 5 times x to the 2/5. And on the top, we get 12 minus 8x. Okay. So, the top of the fraction is the only place that's going to give us zeros. The only time a zero will happen in the top of our fraction is at 0. The bottom of our fraction, when it's 0, it is undefined. We learned that last year. So we know that two things will occur. If we want the zeros, we look at where the top equals 0. If we want the undefineds, we look at where the bottom equals 0. So we just have two things to solve. Where the top equals 0, subtract 12 from both sides. Divide by negative 8. 12 divided by 8, both of them are divisible by 4, so that's 3/2. So there's a critical number at 3/2. Do I know what that critical number is doing? Is it a max? Is it a min? Is it just one of those weird points? I don't know. Don't care. They didn't ask me that. I'm not going to do that. You can graph it, like in a graphing utility like Desmos, but look at the bottom. This here, if I divide off the 5, I still get 0. The only thing that I can take to a power to get 0 is 0. So there's a critical number in two places. There's a critical number at when x equals 3/2, because that's where the top is equal to 0, and where x equals 0, because that's where the bottom is equal to 0. Now that's probably one of the weirdest types of algebra we're going to see within these types of problems. But I did want you to see those types of problems. Some of the algebra is very straightforward. You know, you're just going to think about where it's equal to 0, think about where it's undefined. Now, we talked about in one of the last slides that if it is a function that has a starting and a stopping point, it's continuous, there has to be an absolute max or min. So how do we find that? So let's look over the steps of how to do that. And then we'll do one example of that today. Well, if we have a closed interval, so it starts at A and ends at B, and this function is a continuous function, there's no screwed up points within that, it's just a nice little smooth curve. Find the critical numbers, just like we just did, but it's probably going to be a little bit nicer since it's a continuous function. So we have those critical values, so it might, be at some number. You're going to find them. We're going to have to plug both the critical numbers in and the endpoints. The largest is the max. The smallest is the min. That's it. Okay? So we find the critical numbers. Any critical numbers that are within that interval, we plug those critical numbers in and the endpoints in. The biggest is the max, the smallest is the min. That's it. So it's a very straightforward process when it's a continuous function. Now, if it's not a continuous function, we have a little bit more work to do. So let's go and do one example before the bell's going to ring. So we have a problem here. We don't want to do this with the graph. We want to do it completely algebraically. And all it says is we want to find the absolute max and minimum values of the function from -1/2 to 4. Well, anytime they ask you to find the absolute max and mins, think about the drawing that we saw. We're going to have to look at where the tangent becomes horizontal. So we have to find the derivative. So the first step you always want to take is to find the derivative. So it's just a standard derivative like we've done in the past. So step 1, find the derivative. Step 2, look at where that derivative is equal to 0. Now you're just going to use your rules of algebra. Usually it's a factoring. So we can factor out a 3x. We set each factor equal to 0. We solve. Now look at our interval. We are only going from -1/2 to 4. Sometimes you'll get a critical point that is not in the interval. This theorem, this idea only works if we're in the interval. We just happen to be that 0 and 2 are both in there. So now what are we going to do? Well, we have to find the function values. So we're going to have to plug in to the original function 0, 2, and the endpoints of the interval, because where you cut it off could be a max or a min. And so we have to also plug in -1/2 and 4. Well, if we plug in 0, you get 1. If you plug in 2, you get -3. If you plug in -1/2, you get 1/8. If you plug in 4, you get 17. So just label them. Well, which is the smallest? Here's the smallest. That's your absolute minimum. Here's your largest. That's your absolute maximum. Now, you can verify it with a calculator, so with a graphing calculator. So if you threw this into Desmos, and if you look only between -1/2 and 4, you see that there is an absolute min at 2, -3. There's an absolute max at the endpoint for 17. Now we're going to practice these a little bit more. We'll probably do a few of them together tomorrow. But here's your homework. We're going to do the odds, 1 to 55, 63, 65, and 69. When is you? Not sure yet. I'll mention. Next week, probably. The very soonest Monday.